Last week we looked at monads, which are an interface to things that we can think of that have the ability to do nothing and to do one thing after the other, as well as doing some things. This week we're going to look at two examples of monads which are extremely useful. The first one is going to be input-output, and the second one will be parsing. So let's first look at input-output. So far in the course, we've not really done any real side effects. We've talked about simulating side effects, but as a great philosopher once said, the philosophers have only interpreted the world in various ways. The point, however, is to change it. So how do we really change the world, but remain in a language that only allows functions with no side effects? So to see why this is a little bit challenging in a programming language which only allows functions with no side effects, let's look at some example programs. So one of the key things we can always do in Haskell is replacing equal things by other equal things. So here's a simple example where this is useful because we can use it to reduce code duplication. So let's say we had this rather pointless function that takes a value x and returns a pair where x is added to 100 in both sides of the pair. Now we can easily see here that the same computation is happening twice. So we might think, well, let's simplify this a bit by writing where z equals x plus 100 and then replacing everywhere where it says z with, everywhere where it says x plus 100 with z. And then this has exactly the same behavior as before. All we've done is said that z is an abbreviation for x plus 100, and then we can use that abbreviation here. And because z is equal to x plus 100, we can replace every x plus 100 that was before with z. Now let's think what would happen if we had a function which could output characters to the terminal. So let's, for the sake of argument, call this function putchar. And the idea is it takes a character and then outputs that character and then doesn't return anything useful. So it just returns this empty tuple type. And let's say we had another function called g that took a parameter, and this time it's going to, let's say, take a character and return a pair of empty pairs, tuples. So it takes a character, and this time we're going to do putchar x and putchar x. So we might expect this to output two characters. So we give this function a character, it outputs the first character, outputs the second character, and then returns the pair of return values from doing that. And again, we might say, well, this is repeated work. So why can't we just say z equals putchar x and replace every occurrence of putchar x with z? But now would this mean the same thing? Now we've only got one putchar x and two z's. So does this mean we output the character once? Or what? So it isn't clear how to write this. And if we were to make Haskell functions do side effects on the side, we would have to change the way the Haskell programs are written and not allow this kind of replacing of repeated values with a common definition. So what we actually do is write putchar with this type. So this is a different type to the one we had before. What it's saying is, to put a character, we take a character and then we return an IO action. So we don't actually do the outputting of the character when this function is called. What it does is it returns an IO action back to the caller, and then when this IO action is handed over to the Haskell runtime system, then it actually does the output. And so the type of this function is going to be, takes a character and returns two IO actions in a pair, both of which return the empty tuple when they're actually run. And if we think back to week 6, where we talked about simulating state and exceptions and so on, this is the same idea, except now we're going to be simulating IO actions by building up this IO action type. So the type of putchar in Haskell is actually char to IO action that returns the empty tuple. And conceptually, at toy level, we can think of IO actions as very similar to the process type in exercise 2. So we can think of an IO action as something that either ends with a value, it does an input, so it reads a character from the input, and then that character is used to determine what the next IO action is. Or we output a character, so a character here, and we carry on with another IO action. And then putchar is the same as the output function. So I'll go putchar prime, because there's already a function called putchar. Sorry, it doesn't return the empty tuple. It's the same as the output function. Get that right. So it does an output of x and then ends. Now, the actual IO type in Haskell isn't implemented as this type IO action, because that would be very slow, and the Haskell runtime system would not be able to optimize as effectively. But conceptually, we can think of IO actions as being a bit like this. Either they end, they request some input, or they do some output. So in summary, as we'll see in the next few videos, Haskell remains a pure language, but also allows side effects. And it does this by not having side effects when functions are called, but by having a special type of IO actions that perform some real-world actions and return values of type A. And we're going to see in the next few videos that we can use the monad interface to combine individual IO actions into sequences of IO actions. Now, actually executing an IO action happens either by typing its name at the prompt in GHCI, or in a standalone program by being whatever action is defined to be the main value.